Assalamu alaikum, everyone. Can you hear me fine?
वालेकुम सलाम सर जी
Okay, okay, good. So today we are going to start with a very new, not so new actually, but a new concept, at least in the context of this course, and that is that previously we have been looking at describing the motion without caring about what causes objects to move or stop. And we introduced quantities, for example, like uh, position vector, velocity, and acceleration, and probably a couple of scalars like the radial velocity and time period in case of circular motion. But nowhere here we had any discussion about the causes of motion. Causes of motion, of course, being force. We had occasionally sneaking in the gravitational acceleration g, which comes from a force, which is due to one of the forces that we are going to discuss later on. But we never talked about that this was specifically in terms of the force. And this is more or less what is classified as kinematics. And in where we look at the motion, we quantify it, we learn how to describe it without worrying about the forces. Now, the next topic that we are going to discuss is, or we are going to start is dynamics. Dynamics is where you have, of course, the description of motion, but in addition to this, we will have more quantities coming in, but the main message is that we would also take into account what causes motion. And we all know very well that it is force. So we would have force coming in and another very important quantity coming in. And then we will have the description of motion, but also in conjunction with force, in relationship to the force. And, and that is basically what dynamics is, the relationship between motion, the quantitative relationship between motion and the cause of the motion, which is force, the quantitative relationship between force and motion. And that's what we are going to learn today. So we know what causes motion is force. And what is force? Well, the everyday definition of the force is that if, for example, I pull on this, if push on this board, that's an action, that's I'm exerting force on this board or on this wall. I can also push, for example, the board upwards. This is force. I can also pull this down, and when I'm doing that, I'm exerting the force on this board, and in response to the force exerted, the board actually moves. But that doesn't always have to be the case, because when I'm pushing and pulling this board upwards or downwards, it's moving. But when I'm pushing against it, it isn't really moving. Doesn't matter how hard I push, it's not going to move. And that's why the force exertion of force doesn't always result in motion. It's important to know. So that is the everyday definition of force. More technical way of describing is the interaction of a body with its environment or with another body. Okay? And for example, in this case, let's say if I have a duster here, when I'm holding it, I'm basically, the duster is the body, and the rest of everything else is its environment. That includes me and the force of gravity. So I'm holding it here, and and then the force of gravity is also pulling it down, weighing it down. So everything other than the body becomes its environment, and whatever interaction an object has with its environment, it becomes the forces. So and it's so and so and interaction, and you can also have, for example, two bodies interacting with each other. For example, if you have If you consider hydrogen atom where the proton is sitting at the middle, and then you have an electron somewhere around this. So the hydrogen atom is constantly, so the proton at the middle of the hydrogen atom is constantly pulling this electron, exerting a force on it constantly. That is the interaction between these two bodies, the proton and electron. So the interaction can be between, or the force can be between two objects, between one and several other objects, basically between one and all of its environment, anything that is in its environment. That is what force is. All right. The quantitative relationship, of course, when I say quantitative relationship, what I mean by saying quantitative relationship is that when you because we know that force causes motion, but how much of force causes what amount of motion, that is very important, because we physicists do not work in qualitative terms, we work in quantitative terms. We want to know that for a given amount of force, what is the response, what is the motion that is caused in response to it. And that is, to describe that, we need a quantitative relationship. And the quantitative relationship between force and the resultant motion or lack thereof was first time formally presented or stated by Newton in 1687. In the year 1687, in his famous book, which is called nowadays Principia. And the Newton's formulation, of course, was based on extensive experimental evidence, extensive experimental data that he himself had, and he relied upon others' work for the experimental evidence, uh, particularly by Galileo. And there is of course, a commonality between the two. You are probably familiar a little bit of history. Galileo died in 1642, and Newton was born in the same year. And there is a similar commonality between Maxwell and Einstein, and I think the year is 1879. All right. So it was Newton who stated the exact mathematical relationship between force and the amount of motion that it causes. And I'm using the term amount of motion in a very loose way, because we would introduce this in more specific terms in a minute. Another important point about Newton's mathematical description of the relationship between force and the motion was that he didn't drive them from anywhere. He did not deduce, he did not drive these laws from anywhere. These laws are fundamental in this sense. They are ab initio, they're first principles, and he only deduced it. So which means is, by looking at the experiments, he realized that anything that moves in the universe follows this pattern. I'm going to describe this mathematically. And usually in such cases, when we have a theory, a fundamental principle, the proof is a posteriori. The proof is not failing of the theory. So a theory is accepted to be valid unless we find an example, which is an exception. Unless we find an exception, we accept the theory to be true. And of course, until 1900, year 1900, approximately until year 1900, that was the case with the Newton's laws, with the Newton's description of motion and force. Okay, because there were no exceptions, and close to the near the end of the century, close to 1900, there were experiments which were showing us that Newton's law are not valid when we go to small scales. And these principles that Newton stated, and today we call them Newton's laws of motion, and that is all that there is on the basic level, or the foundation of what we call today classical mechanics. Classical mechanics, interestingly, the word classical itself is very modern, because nobody called Newton's mechanics uh, classical until we found modern physics or modern mechanics. So when we started learning modern mechanics, that's when we started It's calling the Newton's mechanics classical mechanics. It's also referred as Newton's mechanics. Another important aspect is that what the benefit of quantifying the relationship between force and motion was that we could sometimes undo what we learned from common sense, because since we are born we have a cognitive experience. We see things moving, and we see things falling and moving, and we have also familiarity with the concept of force, because we know when we push things, things move, when we pull things, things move. And then we have a common sense perception of the how universe behaves. And then when we test this common sense against Newton's second law, even in our classical universe, macroscopic objects, anything that we can see, we see that a lot of times the common sense is not correct if we correctly do the mathematics. That is why it's very important to have a quantitative description of the physical universe. Okay, before starting with the Newton's law, that is the Newton's laws, that is the objective of today's lesson, and a few more lessons that would come. I want to first little bit talk about force. So as I said before, whenever we talk about force, this is fundamental, this is very important, and it takes away a lot of confusions if you learn to think about force in a sense that force is always exerted by one body on another. There is always an agency and a subject, right? So you always have force being exerted by one body and another, and then the concept of body becomes very it's not very rigid. What is a body? And we'll talk about it, because I don't want to confuse you at this stage with extending the concept of what is a body, because then you have internal forces and external forces. Okay, but let me first talk about the force. What is a force? There is a very loose classification of forces between contact forces. So one of the class is called contact forces. We will do a lot of problems and examples using these contact forces. What is a contact force? Typically, a push on an object is a contact force. And as the name suggests, it is when the body exerting the force on the body that is being exerted on, the force is being exerted on, they are in physical contact. They are in physical contact. Any force, for example, push is a contact force. In a similar way, if you have a string or chain and you're pulling on something, pull is also a contact force. In a very similar way, if you have an object sitting on a surface, there is a normal force, the force exerted by the surface on the object, and it is always at 90 degrees. It makes a 90 degrees angle with the surface. This is called a normal force. Okay, it's always at 90 degrees with the surface. Then another type of force, when you are dragging an object, when you are dragging an object on a surface, the force of friction, the friction between the surface that resists that dragging, that resists that motion, the force of friction is also a contact force. Any force that emerges due to the contact between two objects is a contact force. For example, I don't know if you can see this. If I push this duster along, there are two contact forces acting on this object. One is the push and the other is the friction. Okay, there is a third force acting on this duster, which is the force of gravity, and that's not a contact force. I'll talk about the non-contact forces as well. Although in the book it says long range forces, but I just do not like the terminology in the sense, because they have a very different range of action. So the non-contact forces, again, as the name suggests, a non-contact forces which acts on a body from a distance. The objects do not have to be in contact with each other. Well, one of the examples is that we have an object away from Earth. It is not in physical contact with the surface of Earth, yet the force of gravity acts on the object and pulls it down, weighs it down. Okay, so there is no physical contact between an object and the surface of Earth. So this is a non-contact force. Another example of a non-contact force is, for example, if you put a north pole of a magnet against north pole of a magnet, and if you try to bring them together, they push each other's apart without being in contact. So magnetic force is a non-contact force. If you have two charges, two similar charges, you know that from your high school physics. If you try to bring them together, they push each other apart, and the opposite is true for the opposite charges, that they pull together. So they start exerting the force on each other at a distance, at a finite distance. It's another. Electric force is a non-contact force. Magnetic force is a non-contact force. Gravity is a non-contact force. All right. So there are a couple of other non-contact forces, but I'll just let me introduce the concept of force in a little bit of historical perspective as well. Let's say when 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 Newton was working, the only non-contact force probably he was familiar with was either magnetic force or a gravitational force. Later on in the era of Maxwell, probably Maxwell was aware of at least three forces, non-contact forces: gravity, magnetic force, and electric force. And this was Maxwell which unified these two forces. Maxwell showed that these forces are nothing but the facet of the same reality. It's just the same force. They are not distinct. And he reduced the three-force picture of universe at his time to a two-force picture. And of course, these are fundamental forces, right? And he said it is nothing but an electromagnetic force. It is the same force. So we left with two forces, and then much later in the 20th century, we discovered two new forces. One is called the weak force, and they act at a very small scale, at a microscopic scale. This is responsible for radioactive decay. And the strong nuclear force. So now we have again we have again four forces: gravity, electromagnetic force, weak force, and the strong force. And then it was Abdus Salam and Weinberg which unified the weak force and the electromagnetic force, and now it is called electric weak force, not electric weak force or electro weak force. All right. So again, we have the picture of three fundamental forces. These are fundamental non-contact forces. Okay. So what about the contact forces then? Where do they come from? If these are fundamental, what about, are they fundamental? Yes. In fact, if you carefully analyze these interactions at microscopic scale, all of these forces can be traced back to electromagnetic force. Okay. So the only difference is that in this case, macroscopically looking at, we just look at the push and pull, the macroscopic picture, and we call them the contact forces, but they essentially come from the origin is in the electromagnetic forces. Okay. And the reason we have to be in contact while pushing is because the range of electromagnetic force is very small, is microscopic. So when you are actually in contact, if you look very, very carefully, you are never in contact. There is still some distance. You're pushing the object with the electromagnetic forces acting by this object on this object. And if you look very carefully, there is always some distance. The meaning of contact becomes very fragile if you look at microscopic scale. But that's the picture of the forces. That is the forces we would be dealing with. Mostly gravity, probably electromagnetic force. We would not touch these small scale forces. We're dealing with classical mechanics, classical physics, macroscopic scale. All right. I probably you're very well familiar that force is a vector quantity. It's two things that you need to know about a force is yes, we are never really touching anything. Yes, that you push and the amount of force and the direction of the force. So you have to know these 2 points is that the force is a vector quantity, usually denoted by F vector, and it is measured in SI units of Newton. We will come to a formal definition of Newton later on. All right. There is another very important concept of net force. So as you see that force is a vector. So let's say you have an object, okay, and you're pulling it with certain force F1, and you're also pulling on this object with another force F2, okay, and you want to get what would be the net result because you're pulling it with two different forces. Let's say two people are pulling on a block, okay, and you want to find out the motion or the relationship between the force. You can always calculate the net force by simple vector addition of the force. F net, the total force acting on an object, is a simple linear sum of all the forces acting on it, irrespective of which direction. So if you have this situation, or if you have this situation that you're pulling with some force in this direction and you're pulling on the object with some force in this direction. For example, in this case, if the magnitude of the two forces is the same, the direction is opposite, so there would be no motion and the net force would be zero. Only if F absolute is equal to F2 absolute, then the vector sum of F1 plus F2 is always zero, right? So there is a concept of net force. So if we have several forces acting on a body, it's very difficult to trace and solve the problem dealing with each individual force. What we do usually is, while solving mechanics problems, is we try to add forces together and get a net force, and then try to describe its relationship with the motion. This point is okay?
Sir, excuse me, why are we squaring F2?
Oh, sorry. Okay. So this is called superposition of forces or addition of forces. We always deal with a net force, right? So now we begin with Newton's first law. So you're probably familiar with the statement, and it doesn't sound very interesting, but that is not true. So Newton's first law says if net force on an object is zero, net force, sum of all forces, is zero on an object, and if the object is at zero, which means its velocity is zero, it would stay that forever. Okay? That's the first part of the Newton's first law. And this is quite in accordance with our everyday perception. This makes a lot of sense, right? All right. But the second part is more confusing and it's against the common sense. The second part of the Newton's first law says if the net force is zero on an object, and if it is already at the time we are making this observation, we are looking at an object and we are measuring all the forces acting on it, and then we are adding up all those forces. And once we are done adding, we find the net force to be zero. And while we are looking at this object, it was already moving with a constant speed, a constant velocity. Needless to say, that means the acceleration is zero. Okay. If an object is not accelerating and the force is zero, it would continue its motion that way. This is a bit counterintuitive. Now, I know that you have had your high school physics and you're familiar, because when we look in our everyday experience, when we push objects, when we exert force on them and we put them in motion, they stop unless we keep exerting the force. So this is in the common sense is in contradiction to the second part of the Newton's first law, that that objects actually need to continuously move an object, you need to exert a continuous force. And the reason is because
Sir, frictional force is acting on it.
the force of friction is slowing it down. If we had a magical way of getting rid of friction, and once we set an object into motion, it would stay in motion. And you can do this experiment in deep space where there is no friction, no air resistance. If you set an object into motion, it stays into motion. Okay, and those of you who play console games and have some idea that if you are playing a console game in the vacuum, you have to exhaust to brake in the forward direction, right? Because there is no friction. And but if you think of this, if you look at this, and if you're familiar with Newton's second law, for example, which I'm going to write before time, which is a relationship between mass and acceleration. Right? Now, if the force is zero, acceleration is going to be zero. Doesn't it look as if the Newton's first law is a special case of the Newton's second law? Hmm? So it looks like, because you have everything here. When we have zero force, you have zero acceleration. That means both the zero velocity case or the constant velocity case. But that is not the case, and the first law is not trivial, is more than that, and it's very important that we appreciate its importance. I'm going to spend next 10 to 20 minutes on convincing you of the importance of Newton's first law, and it's very useful, not just in this course, later on as well.
Excuse me, sir. ये जो आपने इक्वेशन लिखी है F इक्वल्स टू ma, इसमें हम ये भी तो अज्यूम कर सकते हैं कि अगर हम एक स्पेसिफिक ऑब्जेक्ट का मोशन देख रहे हैं तो थ्रू आउट द मोशन उसका मास तो कांस्टेंट ही रहेगा, तो फोर्स इज डायरेक्टली प्रोपोर्शनल टू एक्सेलरेशन.
ये दोबारा बताएं.
मैं कह रही हूँ ये जो आपने अभी इक्वेशन लिखी है फोर्स इक्वल्स मास इनटू एक्सेलरेशन, तो अगर हम किसी स्पेसिफिक ऑब्जेक्ट का मोशन देख रहे हैं तो मोशन के दरमियान उसका मास तो सेम ही रहेगा, उसका मास कम ज्यादा तो नहीं होगा. तो अगर मास कांस्टेंट रह रहा है तो हम ये कह सकते हैं कि फोर्स इज डायरेक्टली प्रोपोर्शनल टू एक्सेलरेशन according to this equation.
Yes, but I don't like this way of saying, and actually I don't like writing the Newton's law. It should be written like this, in my opinion. If I was the one to write, I would always write it like this. Okay. Acceleration is directly proportional to the force, not the force is directly proportional to the acceleration, because force is the cause.
मतलब सेम चीज ही हो जाएगी ना, क्योंकि फोर्स अगर एक्सेलरेशन से प्रोपोर्शनल है तो ऑटोमेटिकली एक्सेलरेशन इज डायरेक्टली प्रोपोर्शनल टू फोर्स एज वेल.
For example, I'm exerting a force. Do you see an acceleration?
आप exert कर रहे हैं force, no.
So
सर इसमें ये है ना कि आप जो force exert कर रहे हैं वो आपकी normal force के equal है, तो इस वजह से there is no acceleration.
yes, but यहाँ भी तो मेरी normal force मेरी equal है ना, यहाँ तो motion हो रही है.
नहीं, असल में इस बार नॉर्मल फोर्स आपकी और उसके, इस बार नॉर्मल फोर्स बेसिकली डस्टर और उसकी सरफेस की, और वो और आप जो फोर्स अप्लाई करें वो परपेंडिकुलर है ना, तो इस वजह से आई थिंक, समझ रहे हैं?
हाँ लेकिन हाँ ठीक है मैं समझ रहा हूँ, लेकिन असल में आपको ये समझना चाहिए कि यू कैन हैव नॉन जीरो फोर्स एंड स्टिल जीरो एक्सेलरेशन. ये मैं कह रहा हूँ, व्हेन यू पुश ऑन समथिंग वेरी हैवी you are exerting a force and you don't get an acceleration. ठीक है ना?
सही सही.
तो इसलिए the better way to state is acceleration is proportional to the force, not the force is proportional. And force is caused, this is a response.
सही.
ठीक है ना? This is a consequence. Acceleration is a consequence and is not always non-zero.
आप बेसिकली ये कह रहे हैं कि acceleration is caused by force but force is not caused by acceleration.
Yes.
सही सही सही. सही.
All right. So okay, so just keep this in mind. And now imagine that you have you're sitting in a bus, all right? And somebody's at ground standing here, and you are inside the bus, and you are all strapped up. And then you have, let's say, an apple here, okay? An apple here at the floor, right? Now you're moving with a constant speed. The bus is moving with a constant speed, let's say of 10 meters per second. And you have an apple lying on the floor in the aisle, okay? And you are measuring now the velocity of the apple, okay? What are you measuring actually? What is the value? The ground observer is measuring the speed of the bus to be 10 meters per second, the bus, and the ground observer is measuring the speed of every one of you, bus, you, and the apple, everything, and in all cases is getting the answer 10 meters per second. Okay, let's call this AB, BAC, right? Our original notations is equal, is measuring 10 meters per second. Carefully. Now the driver applies brakes, okay, and quite sharply so. What would happen?
सर वो जो आपका एप्पल है, it would move forward.
It would move forward. So, okay, sorry, one more thing. But what was the velocity of the apple before the application of brakes with respect to the observer? What was BC? The speed?
10.
0? No, with respect to the observer inside the bus.
उसके हिसाब से 10.
0. When the brakes are applied, okay, what is the velocity of the immediately? What is the velocity of the apple, the VBC?
-10 हो जाएगी.
Sir, 10 ही होगी. Forward direction में जा रहा है.
It's
Yes,
10-0 because
10
he's also moving.
10 hogi if it comes to rest, but let's say it would be non-zero, eh? It would be moving with some velocity, right? All right. Now what has happened? The apple has accelerated. Do you agree with this?
Yes.
It has accelerated. It has gone from zero velocity to a non-zero velocity. It's moving forward, right?
No, sir.
Why not?
I don't think it has, because वो तो हम लोग inertial frame में थोड़ी हैं अभी, तो we can't measure the speed. अगर हम लोग observer हैं who's measuring the speed to be 0, हम लोग inertial frame of reference में है ही नहीं, तो हमारे लिए तो 0 है उसकी speed, लेकिन for an inertial frame of reference
Okay,
0 नहीं है, तो technically there has been no acceleration.
hold your horses. Okay, hold your horses. You can measure the speed. Okay, so
अच्छा.
but even if you can't measure the speed, you're seeing it going away from you, right? Or don't you see when you're riding a bus and the brakes apply, when the brakes are applied, don't you see objects rolling forward?
Yes, sir.
So you do see, and you see that the objects were at zero velocity with respect to you, and now they are accelerating.
जी.
That's a common experience, right? You have objects when you have things in your car and you turn sharp, you see things flying towards the radial direction, or if you apply brakes too quickly and you have a book on the seat next to you, it slides forward, right? It happens. So that's what I'm trying to say. With respect to this observer, the one
B
right.
is bus and C is apple.
Yes, C is apple, B is bus, or yourself, the one person strapped inside, and
Okay,
the A is the observer on ground. A, B, C. Okay. Now, so you're convinced that the apple has accelerated with respect to this observer. Is there any force acting on this apple with respect to this observer?
No, sir.
No, sir.
There is no force that is pushing it forward. Okay. So what has happened? The Newton's first law has failed with respect to this observer, hasn't it? Because
Yes.
Yes, sir.
there is no force acting on this apple, and it's sliding forward. However, जी क्या सवाल है राफे?
तो सवाल ये सर वो बस ये कहने का था कि वो ऑलरेडी एक स्पीड में था बिकॉज ऑफ फ्रिक्शन की फोर्स. अब उस पर ब्रेक नहीं लगी तो एक तरह से तो फोर्स अप्लाई हुई थी तो वो चला ना. तो अभी भी उसका फर्स्ट लॉ मतलब एक तरह से उसके पहले फोर्स अप्लाई हुई भी थी तो उसकी ये स्पीड थी ना. मतलब ये
नहीं जब कांस्टेंट स्पीड होती है नहीं राफिक कांस्टेंट स्पीड की बात कर रहे हैं 10 मीटर्स पर सेकंड आपने किया एक्सेलरेट ठीक है लेकिन जब आप कांस्टेंट स्पीड पे चले गए तो आपकी फिर फोर्स जीरो होगी नेट फोर्स जीरो होगी अगर ठीक है ना अब कांस्टेंट स्पीड से जा रही थी बस कांस्टेंट स्पीड से जा रही थी बस ठीक है.
सर एक सवाल है अगर हम ए के पर्सपेक्टिव से देखें तो कोई फोर्स लग रही है सी पे
किसके पर्सपेक्टिव से
जो ऑब्जर्वर है बाहर
हाँ अच्छा ग्राउंड ऑब्जर्वर जो है finds it very natural doesn't find it very odd because what ground observer is saying ground observer would see कि bus is decelerating the apple is just continuing its motion with the same velocity as it was doing before. So there is contradiction between the observation of two observers. Okay? The observer on the ground would see that bus is slowing down, okay? It's decelerating, it's slowing down, and the apple is not doing anything, and he doesn't find it contradictory because he's saying, okay, bus is slowing down, but the apple is just continuing its motion with the same speed. Before, both were moving with the same speed. Now bus is slowing down and apple is continuing its motion. The outside observer, the stationary observer outside the bus doesn't find it contradictory, although it does not mean he suddenly sees a force, but he doesn't see it accelerating because remember, the apple was already moving at 10 meters per second with respect to this observer and it still keeps moving. It's not accelerating from the observer on ground's point of view, is it?
No, sir.
So the outside observer doesn't see it accelerating and doesn't have to figure out a force. But the problem is for the observer inside the bus, because the inside observer sees it accelerating and cannot figure out a force. And that is when you see the Newton's first law fails. Okay. So that is the point that Newton's first law says that there are two types of frames. Okay. And then by these observers, I can safely call them frames of reference or a coordinate system from where you are making a measurement. Okay. And Newton's first law says that it's possible to have inertial frames of reference. And what is an inertial frame of reference? I'll explain in a minute. What is an inertial frame of reference? And let me say this in a different way. An inertial frame is the one that if you place an object in it, an inertial frame of reference, or if you place an object with respect to it, if there is no force acting on that object, it would not accelerate. And if it is accelerating, there is always a force acting on it. Okay, let me say this in use another example. For example, you are floating in the deep space, okay, with some velocity with respect to, let's say, I mean, let's say that the frame of reference is set on you. So you are floating in the space with 0 speed, okay? Because I choose the frame of reference to be set on you, and then you have an apple next to you again, floating in space, and the velocity of apple with respect to you is 0, okay? So both of you have the same velocity, and with respect to each other, the distance between the two of you is not changing. Okay, both of you are not accelerating with respect to each other. Okay, and let's say then there is a spaceship which is approaching with a constant speed initially. Okay, v is constant. Okay, a constant speed is not accelerating. When you make a measurement while sitting in the spaceship, okay, of Apple or this observer, you will see that they are moving towards this object with 0 velocity, with the same speed as the spaceship, because spaceship would think that they are coming towards me, but it doesn't really matter who is going towards what. It's irrelevant. It's because it has a constant speed, okay, is approaching these two objects with a constant speed. So either you make a measurement from here, a moving observer with a constant speed, or you make a measurement from here, a non-moving observer on the speed of the apple. In both cases, you will find that there is no acceleration, right? And in both cases, you would find that there is no force acting on them, on this object. Okay? Well, you're in deep space, there is no force acting on it. Now imagine the next case, that the spaceship starts accelerating. Its speed is not constant anymore. Right? Now, if you make a measurement from this frame on the apple, you will see that apple is not accelerating. Okay? Because it's constant with respect to you. It has the same speed, is not moving, nothing has changed. Just the spaceship has started accelerating. So your point of view in this case would be that the acceleration is 0, as it should be, because there is no force acting on this apple. But what about the observation of the person in the spaceship? Now, spaceship itself is accelerating, but if when this spaceship makes a measurement of apple, it would appear to the observer here in the measurements that as if this apple is accelerating. The acceleration is not 0, same rate towards the spaceship. Okay. But now if you ask this observer, where is the force that is causing this acceleration? There is no answer. There is no force. Okay.
सर मैंने आपसे पूछना था कि आपने कहा है कि जो स्पेसशिप है इट्स मूविंग एट अ कांस्टेंट स्पीड, और फिर आपने कहा है कि वो एक्सेलरेट कर रहा है, और वो जब एप्पल को देखेगा तो उसको भी यही लगेगा कि एप्पल इज एक्सेलरेटिंग टुवर्ड्स द स्पेसशिप. तो अगर हम कंसीडर कर रहे हैं कि इनकी वेलोसिटी कांस्टेंट है, तो कांस्टेंट वेलोसिटी पे अनलेस दे आर मूविंग द डायरेक्शन, तो इनकी मतलब एक्सेलरेशन प्रोड्यूस कैसे हो रही है अगर वेलोसिटी कांस्टेंट है?
नहीं, देखिए मैंने दो केसेस लिए. पहले केस में कहा है कांस्टेंट व्हेन दे बोथ ऑब्जर्वर्स एग्री ऑन दिस ऑब्जर्वेशन, नो फोर्स नो एक्सेलरेशन. सेकंड केस में v नॉन कांस्टेंट है, ये देखें ना. Now I'm talking about the second case, okay? And in the second case, in the second scenario, the first observer measures acceleration to be 0. And the second observer, the one in the spaceship, measuring the acceleration of Apple, measures it to be non-zero. This is a contradiction between the observation now by two observers. One is accelerating and the other is not accelerating. Okay. So, and again, here there is no force. You cannot, there is no explanation of this acceleration. Okay. So what is an inertia? So it is what Newton's first law signifies is that it is possible to find or set or define inertial frames. Inertial frames is that an object does not move with respect to such a frame unless and until acted upon by a force. Okay. An inertial frame is such that once you are in inertial frame, either you have an explanation or for force or you are not accelerating. As simple as this. If you are in an inertial frame, either you have an explanation where your acceleration is coming from in case you are accelerating, or you are not accelerating. Those two cases, this is what defines an inertial frame. So if you define a frame of reference and you place an object, you start measuring an object's position, velocity, acceleration, everything with respect to this coordinate system. Either this object is not accelerating, which means moving with a constant speed, or if it is accelerating, if A is non-zero, then there is a corresponding force that is causing that, and you know that force. If you have an explanation that of the acceleration, or it is not accelerating, such a frame is called inertial frame. Okay, and Newton's laws are only valid in inertial frames. In non-inertial frames, Newton's laws cannot be applied, and the first law in a way establishes that you can define inertial frames, and then that's a qualifier for the next two laws to be applied. So you can only apply second and third law if you have an inertial frame of reference. That is the most important message of today's lesson. Is this clear?
Yes, sir.
An inertial frame itself can be at zero velocity with respect to another frame, or it can be, or with respect to object, or it can be moving with constant speed. For example, even in this case, when the spaceship was moving with the constant speed, both the spaceship and this observer were inertial frames of reference, okay, or were the inertial observers. Once we allowed the spaceship to accelerate, then the spaceship become a non-inertial observer, and then the Newton's law were no more valid, because you were measuring acceleration of an object which had no explicable source of force acting on it. All right.
Yes, sir.
Any questions about this? This is not very easy. So if you have any questions, please.
सर इस inertial frame का एग्जांपल देके बता सकते हैं जैसे उस बस के अंदर was the bus an inertial frame?
Then the moment you apply the brakes, the bus became a non-inertial frame. Okay. So the moment you applied the brakes, the bus became a non-inertial frame again, because you had acceleration and no explanation for the force. But this ground observer remains a non-inertial observer. Inertial observer.
तो जब inertial frame खत्म हो गया तो Newton's laws don't apply.
No, Newton's law do not apply.
Okay, sir.
Okay, because if you apply still Newton's law, you would have to account for the acceleration in this frame. You are getting some acceleration, right? And now, as I said, from the definition of the second law, whenever there is an acceleration, there has to be a force. So you would have to account for the force that is causing that acceleration. So where is that force coming from? There is no such force here. Okay. So first law, in a way, acts as a gatekeeper for the Newton's second law and third law. So in reality, for example, how about Earth? Is it an inertial frame? Is Earth an inertial frame? So if you see that, yes, Earth is not an inertial frame. Both answers are correct. Very strictly speaking, somebody please mute. Abdullah Ehsan. Abdullah Ehsan, please mute. So if you're speaking very strictly, yes, Earth is not in inertial frame. Any explanations?
Like वो constantly move कर रहा होता है ना at a constant speed.
That's but that's the point.
Sir,
If
it
an
has
object is moving, if an object is moving at a constant speed, then it's an inertial observer. It's an inertial frame of
Sir,
reference.
it is accelerating because it's in an elliptical orbit to be exact.
Yes, we did one problem in one of the exercises that Earth experiences an acceleration due to spin motion of 0.03 meters per second, right? And then it has another acceleration that it experienced due to its rotation around sun of 0.06 meters per second square. So it's not strictly speaking an inertial frame of reference because it has these two components of acceleration. But the numerical value of these components is so small that any failing or any error in our computation while using Earth as a stationary, as an inertial frame of reference are going to be very small. And otherwise, if you're making more precise calculations, then you will have to add corrections to your equations. Okay, for Earth being a minutely non-inertial frame of reference. But for our purposes, it's perfectly safe to assume Earth being an inertial frame of reference. The uniform motion, the motion with the constant speed is fine for an observer. Okay, it's perfectly a fine inertial observer. It's only when the frame of reference is accelerating. Yes, Ahmed?
Sir, could we say that for objects on Earth, the Earth is a perfect inertial frame? Because relative to the Earth, dono objects, like relative to the Earth, was inertial. Like if we're measuring objects on the Earth itself.
I mean, if it really depends, because if the object is part of the Earth, then that's fine. But if you're looking at a moving object, for example, if an object is falling freely on Earth, and if these accelerations were significant, if you were making the measurements, and if let's say that there is a gravitational acceleration that is downwards, and there is a force for that acting on this object, and let's say that I'm not sure about the direction of these accelerations. For example, one of them would be towards the center of Earth. I think the one due to spinning, right? So now there will be a problem, because when you measure the acceleration of this object, you would see this accelerating at this acceleration, not at g. Okay. And then there is no explanation for this additional acceleration while you are observing from Earth, if the magnitude was of this was large. So object freely falling on Earth, strictly speaking, there would be an error in the measurement. Okay.
So sir, if we are considering the error, then it is a non-inertial frame. और अगर हम error
No,
ignore
because
कर दें
we said
pre-inertial frame.
the numerical magnitude is so small, so we would always assume Earth to be an inertial frame for our purposes because the accelerations are very small.
Okay, sir.
Okay. All right, and then I would now introduce the second law of motion very briefly. So we have very usually F is equal to ma written. Okay, and this is best to write it like this. Okay, so acceleration is proportional to the applied force, the applied net force, of course, and it's scaled in a way by mass, because for a given force, a lighter object would accelerate more and a heavier object would accelerate less. And that also takes us to the definition of mass. What is mass in this sense? Not just Newton's first law fails in relative frames, in non-inertial frames. All laws would fail in non-inertial frames. Yes?
Force per unit acceleration होगा mass. आपको मेरी
Sorry?
आवाज आ रही है?
जी.
मैं कह रही हूँ कि इस इक्वेशन के हिसाब से तो मास की इक्वेशन, मास का डेफिनेशन होगी ना फोर्स पर यूनिट एक्सेलरेशन.
Yes, force per unit acceleration. Or you could also think, for example, if you apply a force, right? And a given force, let's say of a given magnitude, 10 Newton, on an object of 1 kilogram, okay, you would get a certain amount of acceleration. And then if you apply same force on an object of 2 kilograms, the acceleration would halve, right? Because now you're applying. So in a way, you can think of force to for mass as a resistance to the motion. And mass is a property of matter that resists change in its state of motion. All right. So the accelerator. So we will talk more about in the next lesson, in more detail about this. So, but this is basically is a quantitative relationship between force and acceleration for a given amount of force and for a given object, of course, because mass will tell you what the object is, and that you can produce a certain amount of acceleration. This is a quantitative relationship. First law, Newton's law, in a way sets the stage that you can apply the Newton's laws only in inertial frames. You cannot apply them in non-inertial frames. And it also kind of qualifies that inertial frames do exist. And then once you have specified that we are working in an inertial frame, then this equation is true, that for a given amount of force, you can produce this much of acceleration. Okay, with this, thank you very much. So if there are any questions, I'll be happy to answer.